So now we will talk about orthogonal frequency division multiplexing, and the OFDM implementation leverages the hardware implementation of fast Fourier transform uh, algorithms to design your transmitter and the receiver. Uh, that is the key things, as mentioned in the last video, that the key bottleneck in the concept, in the implementation of the concept of the multi-carrier modulation, was that you required capital N RF chains or independent receivers to implement that very simple concept. But you can make use of hardware implementation, of IFFT or and IFT, FFT, sorry, to 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 design your transceivers. So that is the key point here. That so this OFDM made use of these simple hardware implementations of discrete Fourier transform. IFFT is nothing but inverse discrete Fourier transform, and it's an algorithm which is called the inverse fast Fourier transform algorithm, which implements inverse discrete Fourier transform, and FFT is an algorithm to implement discrete Fourier transform. So, so let's see how OFDM manages this, how it can design the transmitter and the receiver, making use of these hardware implementations. So let's start with the definition of discrete Fourier transform. So discrete Fourier transform uh, of a signal x of n. You have a discrete time signal x of n, and if you want to compute what is the discrete Fourier transform of this signal x of n, it is defined as, by the way, and this definition is specific to the author of this textbook, because there is a scale factor which is different from the general definition of discrete Fourier transform. So the author, she makes use of this scale factor of 1 over root n, so that you have the same scale factor for discrete Fourier transform and inverse discrete Fourier transform. So the definition for the discrete Fourier transform used here is that is 1 over root n summation um, n equals 0 to capital N minus 1, and then you have this x of n times e to the power minus j 2 pi kn over n. So this is the definition of discrete Fourier transform. So in most of the textbooks, you won't have this scale factor of 1 over root n. Right? Here you have this factor of 1 over root n. This means, in other words, this is root n times the discrete Fourier transform of this, and hence you would because so you would have a factor of 1 over n in the inverse discrete Fourier transform, so that that thing has been taken care of. That is, by defining your discrete Fourier transform to be this, you can define your inverse discrete Fourier transform. By the way, this would be capital X of k. Right? So this would be a function of k, because n is consumed in this summation. So this quantity is a function of k rather than n. Right? So this is capital X of k, which is, you can call the frequency components, discrete frequency components uh, corresponding to this time domain function x of n. So this inverse discrete Fourier transform of this function x of k would give you your x of n back, and that would be equals to 1 over root n summation k equals 0 to capital N minus 1 x of k e to the power plus j 2 pi um, k over n times n. So this now is a function of n, right? So it's giving you uh, uh, it's giving you your signal in, because k is now consumed in this summation, and this is a function of n now. So you can focus on this, and you can look at this expression of inverse discrete Fourier transform, and you can then think of this expression as samples of sum of um, capital N uh, capital N modulated signal, right? So this can be thought of as a sum of the samples of a sum of a multi-carrier modulated signal. So you have this x of k can be thought of as a linearly modulated symbols, and each x of k. So you can think of this as sum of linearly modulated symbols, right? And each of these symbols, where x of k is one of those your one of the modulated symbols, and where x of k, each x of k is modulated by this carrier e to the power j 2 pi uh, k t over n t over tn, where your k would be ranging from 0 to n minus 1. You have capital N subcarriers, and you can think of this as a samples of this continuous time symbols, right? So this would be related to each other via sampling frequency, of course. But for a given sampling frequency, you can think of this signal as samples of a multi-carrier modulated signal, where x of k is modulated with this subcarrier e to the power j 2 pi k t over tn, right? And then you take the samples, discrete time samples of this. So uh, so this relation means that if you have this hardware implementation of this quantity, you can achieve this multi-carrier modulation very easily. Right? So that is the most important thing here. That is the fundamental concept, and now the rest is the rest is math, and how would we would go about this. But the key concept here is that this symbol looks like a multi-carrier modulated signal, right? A discrete time version of the multi-carrier modulated signal, and hence you would be able to use IDFT implementation, hardware implementation, to design your transmitted signal. So that is the key. However, there is one problem, you can say, that this IDFT, eh, these Fourier transform pairs are related to each other via what is called the circular convolution. So remember, uh, you, if you have convolution in the time domain, that would lead to multiplication in the frequency domain. However, for discrete Fourier transform, the relation is just not the linear convolution. Rather, this is related to the circular convolution. In other words, if you have x of n as a time domain symbol, and of course you would transmit it in the channel, right? So a circular convolution of x of n with h of n, right? Um, we will define that in a moment. But if you take the discrete Fourier transform of this quantity, that would be equals to x of k times h of k in the frequency domain, in the transform domain, which is different from the actual setting. Because if you transmit the signal x of n into a channel, that would lead to a linear convolution rather than the circular convolution. However, but we want to make use of this IDFT implementation or the DFT implementation uh, to ease out our design. But the problem is that DFT is related to its frequency domain counterparts via this circular convolution and not the linear convolution. So let me define the circular convolution here. It is somewhat related to the linear convolution, but it's a periodic version of that. So if you compute x of n circularly convolved with h of n, that would be equal to summation k over any n x of h of k times x of n minus k, but that would be a modulo n version of x of n minus k, and that would give you a circular convolution where x of n minus k subscript n is modulo n version of x of n minus k, or it's a periodic version of x of n minus k. That means each of these n samples, then they would repeat one after another after n samples. So it would be a periodic version. It would be a periodic discrete time signal with a period of capital N. So that is the problem, right? So you want to make use of this IDFT implementation that calls for that calls that that would mean that if you carry out the frequency domain analysis, that works with the circular convolution, right? But in reality, right, in practice, a signal x of n, if x of n is transmitted, if x of n is transmitted into the channel h of n, then y of n is a linear, which is output of the channel, is a linear convolution, not the circular convolution of x of n and h of n. So what is the solution here, right? So we would make use of what is called the cyclic prefix, and that would convert this linear convolution into a circular convolution, right? So cyclic prefix would be used, and that converts um, linear convolution into a circular convolution. So the key idea here is that you have this signal x of n. These are samples of x of n, right? So let me write x of 0 as x subscript 0. So this is the first sample. Second sample, you would have x of n minus 1. That would be the last samples. This, let me call x of n minus mu, right? We would suppose that the channel has a length of mu, sorry. So h of n has a length of mu. Right? So you have a channel of mu samples. So what you would do is that you would take last mu samples of your x of n and you would put upfront, right, as a prefix, right? And it is called cyclic prefix because it is put in front in a cyclic manner. So what happening is you would have this x of n minus 1 placed here, right? X of minus mu This would be x of n minus mu. Okay. The last mu samples are taken from the end and put as a cyclic prefix upfront into the symbol. So you would call so this symbol would be starting from so so this would you can also call it x of minus mu. You can call this as x of minus 1, and then you would have samples from x0 all the way to xn minus 1. So you would have capital N plus mu samples altogether for this where these last mu the first mu samples are exactly equals to the last mu sample, and you can see that for n between minus mu and capital N minus 1, your x of so if we call this as x tilde of n, so this was your x of n, and once you have done this cyclic prefixing, we call this as x tilde of n. So you can see that this x tilde of n is nothing but a modulo n version of x of n for n between minus mu and capital N minus 1. So this x tilde of n is nothing but x of n modulo n, right? For the range when n is between minus mu and capital N minus 1. Similarly, that would mean this fact would mean that x tilde of n minus k would be equals to x of n minus k modulo n if n minus k is in between minus mu and n minus 1, right? So, um, so that is clear here, straightforward. That would mean, remember your n takes a value from 0 to n minus 1, and remember you would have a convolution, so this k would take values from 0 to mu, right? So if n varies from 0 to n minus 1 and k varies between 0 to mu, right? That means that in this range, you would for this range of n and k, your n minus k would be between minus mu and capital N minus 1, and that would mean that your x tilde of n minus k within this range would be a modulo n version of x of n minus k. So now let's see how this happens. So now if you transmit this x tilde of n into the channel rather than x of n, right? So you do a cyclic prefix and then transmit into the channel. So you have this y of n would be equals to x tilde of n convolved with h of n, right? So that is what it is, right? And that would be equals to summation k equals 0 to mu h of k times x tilde of n minus k, right? But as we have said that n would take values from 0 to n minus 1, k is taking values from 0 to mu. In that range, x tilde of n minus k is a modulo n version of x of n minus k. So you can write this as summation k equals 0 to mu h of k x of n minus k modulo n, and this is nothing but the cyclic or the circular convolution between x of n and h of n. So with the help of this cyclic prefix, what we have done is we have converted this linear convolution of x tilde of n and h of n into a circular convolution of x of n and h of n. So that is the key advantage of the cyclic prefix that has been used. Um, so so now we'll carry on this discussion in the next video.